Life is full of uncertainty. Like when you stop by your friends for game night, will you be able to find a parking spot outside your friend's apartment? Or what are the chances your crush will say yes if you ask them out for coffee? Or maybe even how likely are you to find a box with your kitchenware when moving into a new place? In all of these questions about unknown possibilities, we're dealing with probability, which is roughly speaking how likely something is to happen. And while you might have encountered probability before, there are some pretty important ideas that crop up behind these seemingly simple questions. I mean, mathematically, what even is a probability? Do we calculate the same kind of thing for each of our questions? And how does the math behind probability help predict what will happen? The answers to those questions and more are precisely what we'll be tackling in these next few episodes. I'm Jason Guglielmo, and this is Study Hall Real World College Math. So far in this course, we've been looking at sets, counting, and permutations, which are all ways of keeping track of the different possibilities or outcomes given a collection of objects. That math was helpful for understanding what options exist and the choices we might make based on those options. It also gives us a language and foundational tools for tackling deeper problems. The next couple of episodes will put those tools to use in the world of probability theory, the branch of math where we study different ways to assign numbers to and calculate how likely something is to happen or to be true. And we use lots of what we learned about sets and counting to do those calculations. Specifically, in math, the probability of an outcome is a way of precisely describing the chance something will happen with a number. We usually show a probability as a percentage between 0% to 100%, or a decimal from 0 to 1, where 0 means something is impossible, and 100% or 1 means something is absolutely guaranteed to happen. For instance, when we flip a theoretical coin, there are two equally likely outcomes, heads or tails. So we can say our probability of getting heads is 1/2. Or 0.5, or 50%. Moving forward, we'll stick with decimal probabilities for working things out, and give our final descriptions of probability as percentages, since we usually refer to them that way in everyday conversation. And to avoid constantly having to write the probability of a particular outcome of an event when calculating things, the typical notation is to write capital P, with whatever we're interested in finding the likelihood of inside of brackets. In this episode, we'll cover some of the ways to think and talk about probability. Our questions about parking spots, crushes, and packing boxes all concerned probabilities, but with a closer look, there are some important differences in each case. First, let's return to that parking spot. Now, before we get into calculations, let's just think about this intuitively for a second. You can probably guess that the more often we find a spot, the higher we'd expect the probability to be that we'll find one on some random visit. Here, we're dealing with what we call a probability experiment or random experiment, which in general is a situation where the outcome is decided by chance. Then, to calculate the probability of getting a spot on a random visit, you might look back on all the times you visited your friend, and how often there was a free spot. If you were really dedicated, you could even record whether there's a parking spot or not every time you visit. The type of probability we're calculating with this probability experiment depends on collecting data, or samples about the real world and how often a certain kind of event occurs. That's why here we're finding what's known as an experimental or empirical probability. Like, let's say you visited your friend 16 times, and find a spot on their block 4 times. We can use that information to estimate the empirical probability of finding a spot in general. If we take the number of successful outcomes and divide by the total attempts, we get 4 divided by 16, or 25%. So, based on our sample data from past parking exploits, we should expect to find a parking spot 25% of the time. Put another way, the empirical probability of finding a parking spot is 25%. And this method works for empirical probabilities in general. We calculate the best estimates for the probability of how often a particular outcome happens by comparing the fraction of times that outcome happens to the total number of outcomes we collected data about. And while ordinary people don't tend to collect data on certain parking spots, it's exactly the kind of data that cities actually gather to help improve parking facilities. What's more, we're not always using the past to predict the future with experimental probabilities. Epidemiologists look at the infection rates during an outbreak to estimate the transmission rate of a given disease at the very start. In other words, they use data from the present to estimate probabilities about the past. We can also apply experimental probabilities in other ways, like inspecting a sample of apples in an orchard to estimate what the probability is of any given apple being ripe, which is basically all about the present. Now we'll spend time looking at empirical probabilities more closely and how data helps to understand them in later episodes. For now, it's helpful to know that generally the more data we have about the outcome we're interested in, the better our guess for the empirical probability. But there are other types of probabilities out there, which brings us to our second question about asking out your crush. Here, running a probability experiment and asking them out over and over to gather data isn't socially acceptable. Instead, the probability is based on your confidence that they'll say yes or no, or that coffee's disgusting, but they'd gladly grab a sundae with you. Because this sort of probability is about our personal and subjective confidence in a certain outcome, we call it subjective probability. We won't be looking at these too closely, but subjective probabilities are often used in a variety of situations to make judgments about the future, much like experimental probabilities, though the actual number reflects a personal best guess rather than being based entirely on data. Finally, there's one more type of probability to discuss, which brings us to our question about moving and finding all the kitchen stuff. The first night after moving into their new apartment, everything Evelina and Narek own is in boxes. After a hard day's work and without their kitchen set up, they decide on takeout for dinner to celebrate the big day. Here's the problem. They really want pasta from the much-praised Italian place nearby, which requires their knives, forks, and bowls to eat. But their stuff was hastily packed into identical cardboard boxes, and since they both assumed the other had labeled them, well, none of them are labeled. They could just open all the boxes in the hallway and fish everything out, but they'd make a huge mess, and unpacking the next day would be lots more work. Instead, they want to know the probability of randomly opening a single box and finding what they need inside. If it's low, they'll go for the local Chinese takeout, which comes with environmentally friendly bamboo chopsticks to eat right out of the boxes. To solve this conundrum, we need some details. First off, all their boxes look and feel the same, so every box is identical from the outside. And since some of their stuff is fragile, they won't be shaking boxes to work out what's inside. They have to open them. Secondly, they have 20 boxes in total, and know that 3 of them were each packed with enough utensils and crockery that they could eat pasta. So here's the question we want to answer. What's the probability they can successfully fulfill their pasta ambitions by opening a single box that has everything they'll need? You might already be suspecting their prospects aren't great, since 3 is a lot less than 20. More importantly, by considering this situation a little more, we can also calculate another different kind of probability. First, we know every possible outcome for the event in advance. In this case, the event is opening a box, and the possible outcomes are all the different boxes that could be picked and what they would contain. What's more, we can use our knowledge about each of the different possible outcomes and describe them as a set. In fact, the set of all the possible outcomes of a probability experiment is called a sample space. Sample spaces are extremely helpful, because if we know all the possible outcomes, then calculating a probability becomes a simple matter of counting. We start by counting all the ways the box they open could be a kitchenware box, and all the possible boxes we have. The probability is then the fraction of ways a particular outcome can happen, divided by the total possible outcome. This is what's called a theoretical probability, because it's based on what we know about the situation in theory, rather than data we gathered in an experiment or our subjective confidence. In this case, each box looks and feels the same from the outside, so each box is equally likely to be chosen. We also know 3 of the boxes contain kitchenware, and we have 20 boxes total. So our theoretical probability for finding kitchenware in the first box we open is 3 divided by 20. Or 15%. With those low prospects and not wanting to risk opening more than one box, they decide to go for Chinese food and chopsticks instead. In general, when we have a sample space with a set of equally likely outcomes, the theoretical probability of something happening is the number of outcomes where that thing happens, divided by the total number of outcomes in the set. With theoretical probabilities, we can answer questions without having to collect a bunch of data, and they're useful when the problem we're dealing with has options that are all equally likely. Like in games of chance. Maybe we want to answer a question like, what are the chances I roll a die and get an even number? There are 3 even numbers on the faces of a die, and 6 outcomes in the sample space that should each be equally likely. So using our formula from earlier, we get 50%. But you could still approach the dice question as an experimental probability, and similar to the parking spots, roll the dice a bunch of times and record how often an even number comes up. That can be helpful if the sample space is complicated, or if we want to check the assumptions of our theoretical probability. Like, we might think all the faces of our die are the same and should come up just as often as each other. But if the die was loaded to favor a particular number coming up, the differences between the empirical probability and the theoretical probability could help us work out that something fishy was going on. Another way to think about theoretical probability is using odds. In everyday conversation, we use words like odds, probability, and chance pretty much the same way. But in math speak, when we're talking about the odds for something happening, we're referring to the ratio that compares all the ways that specific things can happen to all the ways it can't happen in a sample space. For instance, instead of the probability of opening a box with their utensils, Evelina and Narek could have considered the odds of finding a box. That's the number of ways they could find a box of kitchen stuff, which is 3, compared to the number of ways they wouldn't find kitchen stuff, which is 17. We write this with a colon and say the odds they find a box with kitchen supplies are 3 to 17. An alternative way to describe odds is to describe the odds against something happening. This is exactly the same idea, but the other way around. We list the ratio of ways something won't happen compared to the way it could. So for the box scenario, we'd say the odds against them finding a box they need are 17 to 3 against. Odds are a handy description when we have a simple sample space where counting outcomes is fairly straightforward. Unfortunately, our probability experiments in the events we're interested in aren't always so simple. Previously, we saw that for more than one event, the possible combination of outcomes can quickly add up. So writing the sample space and counting when we have lots of outcomes isn't always the easiest way to work out a theoretical probability. For instance, what if Narek and Evelina's boxes only opened up from a single side, and were moved into the apartment with a random side facing up? It's kind of like rolling dice and wanting a specific side to come up. In the sample space of all the possible sides a box could have facing up, there's one way to end up with a top face that opens, and 5 ways to end up with the top face that's stuck closed. Now, imagine Narek approaches a random box in their apartment. Using what we know from before, what are the chances the box contains their kitchenware and is also right side up? Well, our good friend the fundamental counting principle tells us that if there are 2 events with different outcomes, the total number of combined outcomes for both events are the number of outcomes for each event multiplied by each other. In this case, since there are 6 possible ways for the box to be facing up and 20 different possibilities for the contents of a box, there are 120 total outcomes in our sample space. Now, writing these out and checking which outcomes have the right side up and the right contents for the box would take a while. Thankfully, we have a tool for making sense of multiple outcomes like these: tree diagrams. Using our tree diagram, we could visualize a sample space or even focus on a specific set of branches since we already know how many outcomes there are total. Only 3 outcomes involve the box being the right side up and containing kitchenware. So the theoretical probability of that outcome is 3 divided by 120. Or just 2.5%. In general, tree diagrams can help us make sense of what possibilities exist for the outcomes of multiple events, and what the corresponding probabilities are. In fact, we're often trying to work out the probabilities in combination of events, like these. All in all, it turns out that uncertainty and random events can mean very different things depending on the context. For our 3 different kinds of probabilities we've seen, experimental, subjective, and theoretical, what we can measure, what we feel, and what we know lead to different perspectives on uncertainty, and each of which require their own set of tools to deal with it. Thankfully, math offers us precisely this, which is exactly what we'll be looking at over the next few episodes. Thanks for watching Study Hall Real World College Math, which is produced by Arizona State University and the Crash Course team at Complexly. If you like this video, give us a like and subscribe. You can learn more about ASU and the videos produced by Crash Course in the links in the description. See you next time.